If you've ever been in a self-driving car, your first experience might have been similar to mine, which is a sense of both amazement and fear as the car weaves around traffic and changes its pace based on the cars ahead of you. But it's remarkable how far technology has come, especially how much information the car can sense so quickly. We really do rely on the ability to recover information from the world around us a lot. Our bodies can sense a variety of things, as can our homes, phones, ovens, watches, smart doorbells, and so much more, all because the information those things gather creates context and enables us to act on something if we need to. But the information we want to sense isn't native to the digital language that our computers use. And in order for any smart car or connected doorbell to work, we need to convert information from our continuous world into discrete electric levels of ones and zeros. Engineers call the device that does this an analog-to-digital converter, or ADC, because it takes information that exists as a continuous analog stream and converts it into a stream of discrete and finite values that we can use in our electronics. As a simple example to explain the function of an analog-to-digital converter, let's think about recording a movie. The film in question originated in the real world, where there is a continuous flow of movement, light, sound, and more. And when the movie is recorded, it's done with a certain frame rate and at a certain resolution. Each frame or sample is taken a certain number of times per second, and each frame has a certain number of pixels in it, recording the intensity and type of light at that point in space. Then combining the two and replaying it recreates the scene. The end result is also digitized and exists inside computers, so the film team can add animation, special effects, before it's presented to you on the big screen. However, the recording also loses some information. It doesn't exactly replicate the real scenario, because the camera could always have had a faster sampling rate or more resolution to better represent the original scene. An ADC works just like this, by sampling a signal in time and recording the value with a certain resolution so it can be processed. Now that you've got the big picture, let's talk about how to sample information. In an analog-to-digital converter, engineers use the phrase sampling rate to mean that every so often we record information. This rate could be once per day, a billion times per second, or anything in between. Now what's interesting is that your sampling rate depends on the information you're recording, specifically the highest frequency signal you care about. The Nyquist-Shannon sampling theorem says that the sampling frequency must be at least twice as much as the highest frequency of interest. You can look this up. An old industry standard for sampling rate for audio applications is 44.1 kilohertz, which is 44,100 times per second. The ADC would sample the microphone while you speak into it. The reason for this is because 20 kilohertz is generally considered to be the highest frequency people can hear up to. So anything beyond that's really just a waste to record. And 2 times 20 kilohertz just gives us about the sampling rate used in many audio applications. Now let's look at this in more detail. If you play a piano note and want to sample it with an ADC at the same frequency as that note, this is what it looks like. Now imagine that we have several samples that we want to use to reconstruct the piano note digitally in our computer. It just looks like a flat line. But if we sample twice as fast as that piano note, we can crudely recover the information we want. But if we go even faster, we get a way better looking wave. Now let's think about a TV's resolution. You would probably prefer a 4K screen to an old 720p display, right? That higher resolution gives much more detail, and a lower resolution means that each sample gives a rougher approximation of the signal you're interested in. If we go back to recording a piano note, but with poor resolution, we get something like this, with only several allowable numbers to represent the amplitude of the signal. Alternately, a higher resolution ADC represents the original signal like so. Regardless of the resolution, the deviation from the ideal value is due to quantization, which is what happens when you convert a continuous value to a discrete value. Now, one last ADC characteristic you might not think about is power consumption. These are electronic devices that consume power when they run and even when they don't. One of the most important things to remember about engineering is that it's all about trade-offs. Generally, for the ADC, increasing the sampling rate and resolution means that the power consumption will go up. Conversely, if we reduce them, then the power will go down. Now this matters if you are using a battery, especially a small one, because a higher power consumption will drain it faster, just like if you use your phone too much. Or imagine a small sensor powered from a tiny solar cell. That device can't generate much power, so your ADC can't consume much power either. So when you step into smart cars, connected homes, or just take a picture with your phone, remember analog-to-digital converters are at the center of them all. But ADCs play only a small part when you want to electronically sense the world around you. You need plenty of other components and systems to make that happen. I'm Henry Bishop, an electrical engineering PhD student at the University of Virginia and part of the Robust Low Power VLSI research group. We design integrated circuits, including ADCs, so low power we can run them from ambient harvested energy from the world around us. So if you want to check out what self-power technology you may see in your life a decade from now, give us a search and check out what we do.